Imagine a system that operates continuously, testing its parameters and rewriting its own instructions to achieve a higher rate of success without human input. This diagram shows the architecture of Andrej Karpathy's auto research repository. To run an autonomous improvement loop, the system requires exactly 3 interconnected nodes: a target file, a set of optimization instructions, and an empirical evaluation metric. In its original machine learning context, the target file is simply a standard training script. This is the baseline document the system will attempt to improve. The optimization instructions node dictates exactly how an autonomous agent is allowed to modify that script. Usually, this means tweaking a hyperparameter. A hyperparameter is a configuration variable whose value is set manually before the machine learning process begins. Finally, the system runs the empirical evaluation metric. It compiles the modified code, measures the model's new accuracy, and generates a score. If the score increases, the system keeps the change. If the score decreases, it reverts to the previous version. This architecture demonstrates that autonomous self-improvement requires a completely closed, measurable logic system. The agent must have a discrete file to alter, clear boundaries for making alterations, and a definitive mathematical threshold for success. Karpathy built this loop to optimize machine learning models, but this exact architecture can be generalized outside of ML scripts to optimize the highly subjective domain of large language model prompt engineering. We map the first node by removing the rigid ML training script and substituting it with a system prompt JSON. JSON is a lightweight file format that stores data structures and objects in readable text. The second node translates the agent's instructions. Instead of adjusting numerical hyperparameters, the agent is instructed to rewrite the natural language constraints within that prompt. The final node requires substituting the internal ML accuracy metric with external empirical data retrieved via an API. An API, or Application Programming Interface, is a set of protocols that allows 2 distinct software applications to communicate and share data. There is a structural difference in execution speed. A machine learning script can compile and test a change in minutes. Qualitative content deployed to external platforms requires a 24-hour cycle to gather statistically significant feedback. By substituting these 3 nodes, we take the highly subjective output of an LLM and subject it to a mathematical optimization process driven by external data constraints. An optimization loop cannot function without a constant ingestion of ground truth data. The system must know exactly how its outputs perform in reality. The cycle initiates every 24 hours using LaunchDo to run an automatically cron job. A cron job is a time-based scheduling utility in Unix-like operating systems that executes commands automatically at specified intervals. Once triggered, the system requests the MetaGraph API to pull exact view counts from the previous day's content. A sorting algorithm then applies to this payload, isolating the top-performing quartile of content, separating it entirely from the bottom-performing quartile. This sorted data routes directly into the central workflow database using an N8N integration. N8N is an open-source workflow automation tool that connects different APIs and databases without requiring complex custom code. With the data secured, the system runs an initial pattern recognition step. It scans the metadata of the top performers to identify recurring variables that correlate with high view counts. Through this ingestion process, raw social media views shed their vanity context. They operate strictly as an empirical loss function for the pipeline. A loss function is a mathematical method of measuring how far a system's current output deviates from the desired outcome. The primary architectural flaw in most self-improving agents occurs during the evaluation phase. Developers frequently rely on an LLM to provide subjective, continuous scoring of its own outputs. Asking an LLM to rate qualitative text on a scale of 1 to 10 causes severe model drift. Model drift is the degradation of a system's accuracy over time as its baseline parameters shift. A subjective 7 out of 10 on Tuesday might mean something entirely different to the model by Friday. This replaces subjective scoring with a rigid 10-point binary matrix. Instead of asking if it's engaging, it asks structural questions. Does the hook describe a transformation, or does it avoid sounding like a press release? The model must output a strict 1 or 0. A secondary LLM, acting purely as an evaluator, processes the daily generated text against these 10 highly specific questions. The resulting binary array is then summed. This generates a clean, integer-based eval score, free of fractional variance. This rigid schema restricts the evaluator model from applying qualitative feelings or vibes to the text. It either detects the required structural element or it does not. Forcing an LLM into a binary schema translates subjective text into stable, machine-readable data, making the generation process optimizable by a standard algorithm. To finalize the loop, the system uses a correlation engine. Here, the internal evaluation score is tested against the empirical reality of the API data. Charting both data streams, a validated winner has a high eval score and high empirical views. A false positive has a high score but low empirical views. Recognizing its internal criteria are flawed, the system automatically rewrites the 10 binary matrix questions. In the prompt execution phase, the system isolates the validated winners. It analyzes the specific traits that cause them to succeed and writes a new JSON prompt incorporating those exact parameters. An automated API push then executes, overwriting the previous day's prompt file with the newly optimized instruction set. The correlation engine ensures the system continuously refines the text it generates, while autonomously correcting its own definition of what constitutes a successful output. Running this system over 5 complete 24-hour cycles yields highly specific mutations in the prompt architecture. This diff visualization tracks prompt evolution. Recognizing announcements yielded poor empirical results, the system shifted toward a curiosity framework. It deleted failing tone instructions, generating false positives, replacing them with universally successful parameters, like framing the topic as a timeless discovery. The resulting prompt relies strictly on mathematically validated instructions, completely eliminating human guesswork from the pipeline. After running this loop continuously for 30 days, the final and most critical output of the system is the continuous research log. The log maintains a permanent, precise record. It maps every discrete mutation of the prompt directly to the resulting shift in empirical data. This log solves the inevitable problem of system obsolescence. When a significantly smarter foundational model is released to the public, existing hard-coded prompts often break or become redundant. Instead of starting from scratch, a developer can feed this log directly into the new model. The new model reads the exact paths of success and failure, instantly adopting all previous systemic learnings. The true value of this architecture lies in the mathematically proven log. It allows you to instantly port months of autonomous, empirical optimization to any future AI model.